All right.
Well, good evening,
I
everyone.
I'm a gray square.
Yeah, what's wrong with you? You're a gray
I
square.
don't have any light on my
Oh,
side of the room, so that's all
oh,
right.
oh,
People don't
well,
have to
okay.
look at me. They'll look at you
All
instead.
right. Okay. Well, I'll tell you what. While we're waiting for you to figure out what color you should be, um, I want to just welcome everybody. You just heard Richard Osier. Richard is one of the astronomers up here at the Chabot Space and Science Center, and I'm Gerald McKeegan. I'm another one of the astronomers up here at the Chabot Space and Science Center, and we want to welcome you. Um, Might be interesting to know, Richard, that this is the 30th time that we have done a virtual telescope program. We've done
That's
it
right.
30 weeks in a row. So, the typical TV season is only 26 weeks. So,
Do you remember what we looked at in number 15?
no.
Neither do I. I have.
Well, I just want to say a few things here. I want to make sure that we acknowledge and kind of give a
Yeah,
shout out to all of the members, the Chabot members, and the Chabot donors. If you'd like to be part of our community, you can join as a member of Chabot by going to the Chabot Space and Science Center website, chabotspace.org. Um, and in fact, if you join between now and December 31st, special thing, we're going to give a free membership to a local teacher for every new membership that gets signed up between now and December 31st. So there's a description, I think, in the comment section there. You can click on that, or you can go to the chabotspace.org website, and you can click on the membership link and join up. And if you don't want to become a member, we encourage you to donate to our program here. There's a donate button on our Facebook page. You can also go to the Chabot website, and there's a donate button there. Um, your donations help us continue producing these programs. In addition to the 30 programs that Richard and I have done, we also do daytime programming for school kids and so on. We've done a total of 75 virtual programs since April. And we want to continue doing that. So we do need your support. Because the Chabot Space and Science Center is not open to the general public right now, the only way we can continue to get revenue is through donations from folks like you. So we want to encourage you to check out either the donation button on the Facebook page or go to the chabotspace.org website and click on the donate button. And also, while you're there, you can learn a little bit more about some of the upcoming programming we have. All right.
yeah.
So,
I also want to mention while you're visiting these websites and visiting, especially the Facebook video archive. For those of you who haven't been able to watch our program every time or have missed out on some of the other excellent virtual programs that Chabot has produced, they're all there on the Facebook video page. So,
yeah.
as well as the YouTube channel, and I encourage you to check them out. In fact, just the other night, Ben Burris did a presentation on the history of science fiction and how it contributes to
Science fact.
ideas of space propulsion. And it was a really great talk. I really enjoyed it. And it's talking about ion drives and how NASA beat the Federation to it by 200 years.
All right. Well, I think people came here to look through our telescopes.
Yeah,
Uh,
probably. So why
tonight,
don't I
tonight,
share?
our
Yeah,
weather is sort of mediocre. We've got
yeah.
some scattered clouds in the sky here, so we're going to be dodging clouds a little bit. The humidity is nice and low, so that's the good news. But we do have some clouds, so you may have to bear with us a little bit. So I think we're going to start with Mars, right?
Oops, hold on here.
Maybe.
There we go.
There it is.
Yep, right where I left it.
Oh, yeah, yeah. Okay, well, Let's see. You got a kind of a close-up image on the right there, and then the normal image on the left. Because we don't have ideal viewing conditions tonight, we don't have a real sharp image of Mars, but you can see some dark features on Mars and some light areas. The dark features represent more mountainous terrain, more heavily cratered terrain. The light features are more desert-like. Um, Mars used to have some very active volcanoes. The volcanoes are still there, but they're no longer active. But when they were, they spewed a lot of dust out into the atmosphere, which settled down more in the northern part of Mars than in the southern part. And it produced those large deserty areas. So you see them as light colored regions on Mars. Um, very few craters in those areas. It's a lot more like being out in the desert. There is one big volcano on Mars. It's the largest volcano in our solar system. It's called Olympus Mons. Olympus Mons is 3 times the height of Mount Everest, and its base is the size of the state of Texas. So it is one huge volcano. It's no longer active, but it's pretty impressive when you see close-up images of Mars taken by spacecraft flying by. It's pretty impressive looking
I want to
object.
mention also that, another reason, although tonight really seeing is the main reason we're not seeing as much detail, the atmosphere is kind of roiling with these high level clouds that we've got. There's also some significant dust storms on Mars this week, so
Oh, well, that would
there that
obscure some
that
things.
will
Yeah,
obscure some things. Yeah,
yeah. So maybe what we're seeing is dust rather than
it could be.
just the
It's probably
fuzziness and
contributing. Yeah.
yeah, yeah. Yeah, that happens. Curiously, it often seems like when Mars is closest to the Earth, that's when it decides to have some global dust storms. So it's kind of frustrating for astronomers. The Earth laps Mars every 2 years and 2 months. The Earth is closer to the sun than Mars, so the Earth orbits faster than Mars does. Um, and every 2 years and 2 months, the Earth passes between Mars and the sun. So if you imagine a line between Mars and the sun, the Earth crosses that line. And that's roughly when we are closest to Mars, and therefore Mars looks biggest in our telescopes. And so astronomers are always looking forward to what we call the Mars apparitions. And it just seems like so often, about the time that a Mars apparition is due, you get a big dust storm on Mars, and it kind of spoils the
Yeah,
view.
that
So
is true.
I think the Martians don't really want us looking at them. So
Yeah.
okay, well, that's Mars. I'm not sure what else we can tell you. If the scene was really good, if we had a really clear image, you might be able to see a hint of the solar or the polar ice cap, the southern polar ice cap.
Let me try something here. I may be able to pull it out. It'll really wreck the color on the rest of it, but
Yeah,
sometimes this
it would
works.
be at
Yeah,
about the
doesn't work.
7 o'clock
Yeah,
position.
I can't pull it out tonight.
No, no. Oh well,
Yeah. Oh well.
it's there. Take our word for it. So, all right. So,
No such thing.
in the past several weeks, we have been looking at the planets Jupiter and Saturn. But what's happened is as the Earth orbits around the sun, we're getting farther and farther away from Jupiter and Saturn. And Jupiter and Saturn are getting farther and farther into the western sky to the point where by this time of the night, they're pretty low in the sky. Uh, and our telescope that we're using here has a limit. It can't view anything that's less than 15 degrees above the horizon. And unfortunately, Jupiter and Saturn are now less than 15 degrees above the horizon. So we're going to have to wait till next year before we get to see them again. But they will be there again next year. So we've got a couple of other planets we're going to show you. Not quite as dramatic as seeing Jupiter and Saturn, but they're planets. So let's see, which one do we want to go to first? How about Uranus?
Sounds
Or
good.
Neptune's getting, yeah, yeah. Yeah, why don't we go to Neptune first, because it's starting to get low also. So,
yeah, I think it's a good idea
all
also for the
right, all right.
clouds.
Hang on just a second here. So our telescope is a computer-controlled telescope. This telescope is our newest telescope here at the Chabot Space and Science Center. It's a 36-inch reflecting telescope, so it uses mirrors instead of lenses. And inside of the telescope, there are two mirrors. The biggest mirror is 36 inches in diameter, which is why we call it a 36-inch reflector. And then there is a much smaller mirror at the front. So the big mirror, the primary mirror, is at the back of the telescope, and it has a slightly curved surface so that when light hits it, it bounces off the mirror as a cone of light rather than bouncing straight back. And that cone of light reflects off a secondary mirror that's at the front of the telescope. It's a smaller mirror. It bounces off that mirror.
Okay.
Hey, there it is.
Not bad.
Yeah.
Let me bump that up
I'm
a
gonna
little bit.
reposition a little bit. So
Yeah,
take another image. We want to get it a little bit closer.
Okay.
Did I see a ring around Uranus?
No, it's that would be. It's also chromatic aberration around
Okay.
Uranus.
Okay.
Hold on, let me lower the exposure a little bit and see how that comes out.
So how long of an exposure are you doing?
It's
10
just
seconds.
a 10 seconds.
Yeah. So even in this image, you can see that Uranus has a little bit of a greenish tinge to it. It's a gas giant planet, sometimes called an ice giant because it's so cold there. And yeah, all right, we get a little closer to the center.
All right.
And by the way, it does have a ring around it.
Yeah, we're not going to capture that tonight.
Yeah. Well, actually, I've got an image I can show you here in a second.
That would be great, actually.
Yeah.
If you could.
Yeah. So one of the cool things about Uranus is planet number 7 going out. It's the Jupiter is number 5 and Saturn is number 6 and Uranus is number 7, and it's pretty far out there, so it's pretty cold, and it has an unusual characteristic. The other planets in the solar system orbit in such a way that the poles are more or less up and down relative to their orbit around the sun. The poles may be tipped a little bit, like Earth's poles are tipped about 23 and a half degrees. Mars poles are tipped about 25 degrees, but in general, they're sort of up and down versus the direction that the planet orbits around the sun. Uranus is very different. Uranus is laying on its side, and it's a really weird effect. And it means that as Uranus orbits around the sun, taking 87 years, I think it is, something like that, it spends a quarter of that orbit with one pole pointing at the sun, and about a quarter of that orbit with the equator pointing the sun, and then a quarter of the orbit, the other pole orbit or faces the sun, and then the fourth quarter, again, it's the equator facing the sun. So it's a really weird kind of orbit and pole orientation, and we think it's because Uranus got clipped by some other object, maybe another protoplanet or something early in the history of the solar system that caused it to tip over on its side. In fact, if I can share my screen, Richard.
Yeah, go for it. Yeah.
All right. You cannot share while the other guy. Oh, now I can. All right, here we go. So here's an image taken by the Voyager spacecraft of Uranus close up. And yes, it does have rings. They're very faint, so we can't really see them from Earth. But like the other gas giants, it spins fairly rapidly on its axis, and that sort of wraps the atmosphere all the way around the planet. So you get these bands. Now, this actually shows more of a tilt than it really has. Its tilt is even less this way and more almost horizontal here. And that's how it orbits around the sun. So it's a really weird effect. And you see it's got a few moons, got one bright moon right there. I think it's, was it Ariel, I think it's called?
Yeah, it's there's Titania, Ariel.
Yeah, I think Ariel is the biggest one.
Gosh, let me see. Yeah, Titania, Miranda, Ariel,
Oh, maybe it's Miranda.
Oberon. Yeah, and there's 27 moons in all.
Oh,
yeah, I
okay.
only know the big one or two there.
All right.
Now, if we go back to our image, I'm going to share again.
Okay.
You can see one of the moons here.
Oh, yeah.
And it's just off to the 8 o'clock position of the planet.
See, that's what I thought was the ring. And I was like, how can we see the ring?
No, no, but at least we can see the moon.
Yeah.
I don't know which one that is, though.
Yeah. So unfortunately, it's very far away, so we're not going to be able to get a much bigger image than this. And if we tried to magnify it anymore, we probably would end up with a very fuzzy blob.
Yeah.
So
more blob than it even is now.
Yeah. All right. Yep. So that's Neptune. Let's go in the other direction on the opposite side from Mars. We're going to go to, actually, you know what? We were just looking at Neptune, not Uranus.
Oh, gosh, you're kidding me.
Well.
All right. Well, how was that? You know, somebody caught that in the Facebook feed where they asked, "Are we looking at Uranus or Neptune?"
We're looking
and
at Neptune.
I answered Uranus because I was, you know.
Okay, let me share the screen again, and I'll show the picture of Neptune. You didn't expect people who knew what they were doing here, did you?
Well, I feel better about when I make mistakes now.
Yeah. Okay, let me share my screen here. It's not letting me share.
Oh, let me try again. Hold on.
I think you need to make me a co-host or something.
Yeah, I'll do that this time. Hold on. Hold on for a moment. I got to do this on the other machine. Make co-host. All right, you are now a co-host.
Oh, all right. Okay, Neptune. Never mind what you just saw. Here's Neptune. All right, so Neptune is another gas giant. It also has a ring, but it's a much fainter one, and its poles are oriented more or less up and down relative to its orbit around the sun. So, but yeah, as you can see, it also spins very rapidly. It has some cyclonic activity in its atmosphere like Jupiter does. And again, this is a Voyager image taken back in the, I think, the late 1970s or early 1980s. All right.
Well, let's go for the real thing now.
Okay.
Now that we've confused everybody, including ourselves.
Yeah. We're going to go to Uranus, right? All right, here we go. By the way, Neptune is the 8th planet from the sun, the 8th full-size planet from the sun. And now we're going to Uranus, which is the 7th planet. Good, right description, wrong planet. Okay, so we should be there. Yep.
All right, let's shoot the same time. See what happens.
It might actually be a little bit brighter, or dimmer, rather.
Now, if it turns out we're looking at Saturn here, I'm going to get angry.
Okay, it says it's done.
Oh, there we go. Nice.
Hey, we found it. Oh, yeah. And I think I see a couple of moons around there.
I see 3, I believe.
Yeah.
There's 2 above. There's one here. There's one here. There's one here.
Okay, so this is really Uranus. I had to look again. Get
Just
myself
to make
so
sure.
yeah. So unfortunately, all the big bright planets, except for Mars, they're all hiding from us right now. So we got to look at these little faint jobbies.
I'll try something here if you don't mind.
Okay.
I'm trying to decide whether we're seeing 3 or 4 moons, and I want to take a slightly less sensitive exposure.
All right. So just want to remind you folks, if you have questions or comments, be sure to put them in the comment section on Facebook. We do welcome those comments.
Well, I think we see 4 moons. So right here,
Oh,
there's
yeah?
one right here,
Yeah.
there's one right here, and there's one right here. I thought we were seeing maybe some kind of weird spike
yes.
effect, but that's
So
not. That's definitely a moon.
those little bumps are actually moons. Yeah.
Yep.
Cool.
Yeah, these are spikes down at the bottom from just the brightness, but
And then I see a
that's
couple
got
of
to be a
hot
moon.
pixels in there.
Yeah, yeah, that's right. My friends are there tonight. And anyway, that's pretty neat.
Okay. Well, I actually am going to be able to identify those moons for you.
Oh,
So
let's do that.
the one up above, yeah, can you zoom in again?
There
So
we
the
go.
one up above, that's Titania. The one up to the left is Ariel. And then the one down to the left is Umbriel. And then the one way down below is Oberon. So 4 moons, pretty good.
Yep. It's nice to have the aperture to do that.
Yeah.
Great.
Okay.
So it's funny. The sky is really strange tonight. So it's opened up a little bit to the east, but it's gotten pretty cloudy to the west. And we were going to try to give you a comparison of a globular cluster and an open cluster, but I don't know if we're going to be able to see M15.
It looks like we might. I can.
Want to give it a shot?
Yeah, I can see Enif, so maybe we can.
Okay, let's try it because
All
it's an interesting comparison.
Yeah. So what, Richard? I'm going to go to a star that we can sync on here, Richard.
All right, let me go to live view.
So we're going to make a pretty big move with our telescope. And although the telescope tracks pretty well, when we make really big moves with the telescope, sometimes it doesn't quite hit the mark perfectly. So periodically, when we make big moves like that, we'll try to synchronize the telescope and the software to get them. Yeah, there we go.
Yep. By doing that synchronization, the telescope knows where it is, and it's more accurate when we make the next jump.
Right. Okay. All right. Off to M15, maybe.
Yeah.
There we go. All right.
All right.
So you're going to have to do a little bit of an exposure here. So M15 is what we call a globular star cluster. It's like a ball of stars out in space. There are about 150 globular star clusters orbiting around the galaxy. And each one has several 100,000 stars in it. The stars in the cluster orbit around the center of the cluster, which is a very dense region. And the cluster itself orbits around the galaxy in a region called the halo. So M15 is about 33,000 light years away. So we're going to be seeing it the way it looked 33,000 years ago. People often ask me,
There we
well,
go.
does that mean it's still there? And yes, it is still there. 33,000 years in star time is not very much. So I'm gonna,
All right, that's not too bad.
no,
Yeah, so it gives you a good idea of how dense that center area is, and you can see a little bit of color in these different stars.
yeah,
And there's several 100,000 of them there,
yeah.
all packed together.
The stars orbit around the center in highly elliptical orbits. So they go in very close to the center, they swing around the center going very rapidly, and then they swing way out to the fringe of the cluster. And as they go out, they slow down and eventually they reach a point where they start to turn around and come back in. That's when they're moving the slowest. And then as they come back in, they speed up again. And it goes through this process over and over again, held to the cluster by the combined gravity of the cluster. Now, the cluster is about 120 light years across. And I want you to kind of imagine for a second what that means. Um, the closest star to our sun is 4 light years away. So if stars were spaced at 4 light years, across a space of 120 light years, you would expect to find 30 stars spaced 4 light years apart. But here we've got thousands of stars in the space of 120 light years. And that means it's really dense. There are really a lot of stars, especially close into the center. In fact, if you lived on a planet orbiting around one of these stars, you wouldn't have a nighttime because there would be so many stars so close to you, they would just light up the night sky. So, it might get a little darker when your planet rotated away from your own star, but it would never get fully dark like we have here on Earth. So, very different environment. These stars are also very old. We think they're among the first stars to have formed when our galaxy was first forming. So they're more than 10 billion years old. In fact, closer to 12 billion years old. All right. So
Great.
this is what we call a globular star cluster. It's a ball of stars with all of the stars orbiting around the center of the cluster. So we have another cluster we'd like to point at. Hang on.
Yeah, and that should be readily visible now. So we're gonna go to
completely different part of the
yeah,
sky.
completely different part of the sky. So we're gonna have to take a stop midway, I think.
Yep.
And we're gonna go to an open star cluster. Now, an open star cluster is a much more modest deep sky object, and these are groups of stars that formed out of the same molecular cloud, the same ball of hydrogen gas during the star formation period in that region of the Milky Way galaxy. And it's far fewer stars than a globular cluster. Here, let me put up the bullseye here for a sec. There you go.
Okay.
It's far fewer stars than a globular cluster. We're looking at, hundreds of stars, not, hundreds of thousands of stars. Sometimes they have very interesting patterns, and there's a group of fairly impressive ones in the constellation Auriga, and it's well positioned for us tonight to take a look. So it's M37, right?
Right. Yeah.
Okay, M37. So the M in M37 means it was first cataloged, not necessarily first discovered, but first cataloged by Charles Messier, the French astronomer, in the 1700s. And there's 102 Messier objects that are all fairly bright. You can see them all through a good pair of binoculars or through a small telescope, even in the city. And M37 It happens to be an open cluster, but there's all kinds of things in that catalog. There's open clusters, globular clusters, galaxies, double stars even. All right.
This is another intermediate
Yeah.
point here.
Yeah, I figured as much.
We're going a long way, so I'm making a couple of stops here.
That looks good.
And we're going to buzz right by the Pleiades, which is yet another open star cluster.
Yep. Or the Subaru, as it's known in Japan.
Yeah.
And they obviously named the star cluster after the car, right?
Right. Okay, I think we're going to hit it this time.
All right.
Watch your cables.
Yep, I'm watching it. I think we're good.
It's relatively clear in that part of the sky.
Right. All right. We'll have to do an exposure for this, obviously.
Yeah.
So hold on for a moment. And we will. That is not the open cluster.
No.
That's the last thing we were looking at.
So an open star cluster is actually, unlike the globular clusters that are out in the fringe of the galaxy, out in the halo of the galaxy, open star clusters are within the galaxy, and they represent stars that formed at roughly the same time out of a huge cloud of gas and dust. That's how stars form. Big old clouds, they condense and they form a whole bunch of stars within the clouds, and then eventually the cloud dissipates away and it leaves behind
there we go.
cluster
Very
of
nice.
stars. Yeah, actually, gonna go
probably move it
a little north,
a little bit north. Yeah.
All right, if you want to try it again.
But that's not bad.
Yeah. So anyway, the cloud condenses, it forms new stars in it, and then the cloud dissipates and it leaves behind a whole bunch of stars relatively close together. Not as close as in a globular cluster, but close enough together that they're all moving as a group through the galaxy. They orbit around the galaxy as a group, and so we see them as these little clusters of stars. And the thing that distinguishes them is that they are not kind of a uniform pattern. So when you saw the globular cluster, you saw that it was dense in the center and less dense as you moved out from the center, kind of like a ball of stars. But these open clusters don't have any particular shape to them or pattern. They're just a whole bunch of stars very close together. And the thing that's interesting about them is since they're all about the same age and about the same distance away, any differences that we see in the stars are intrinsic to the star. You know, if you just randomly start looking at stars and you see differences in brightness or differences in color, you have to ask yourself how much of the differences that I see are because of the true characteristics of the star, and how much is because it's farther away or closer or younger or older. You don't have that with open star clusters. They're all about the same age and they're all about the same distance. So if one star is brighter than the other, then you know that star really is brighter than the other stars. If one star is bluer in color, you know that star is hotter than the others. And by studying open star clusters and characterizing the stars in them, because we can actually see their intrinsic properties, it builds up a catalog of star characteristics based not on size or not on distance or not on age, but strictly on their physical appearance. And we can then use that to characterize other stars that are not in open clusters. And that's one of the techniques that astronomers use to develop, a scenario for how stellar evolution works and why some stars look different than others, why they look, different colors or look brighter, even though they seem to be farther away, and so forth.
It also begs the question on what caused these intrinsic differences in the first place.
Right.
So there might be in those molecular clouds that provided the material for this star formation, different areas of density. So there might be more dense regions, which would have created a more massive or hotter star compared to some of the neighbors, which might have been from a lower density region in that cloud. So there's a lot of different theories about why you'll have different types of stars all coming out of the same litter, so to speak. But anyway, this is a
Yeah.
great example. This is a great example because the color differences are dramatic here.
Now, one thing I want to point out, you see up near the top of the frame, you see a brighter star. It's brighter than the other stars.
Yeah, that one doesn't belong here.
Yeah, and it's actually kind of a yellowish orange in color.
Yeah.
Turns out that's actually a foreground star. That
Yeah.
star is closer to us than the cluster. So ignore that star. It's just an interloper.
It's this one here, but the others that are of that color could very well be part of the cluster.
And you can see even in this image, some of the stars are blue and some of them are yellow. A lot of them are white. Those are tell us the temperature of the stars, and from that we can actually determine the mass of the star, because again they're all the same distance and all the same age. So differences in color are a function of how hot the star is, and how hot the star is a function of their mass.
I want to catch up on some of the questions that people have been asking.
Okay.
So Sabina, the color that you're seeing is real. So and Gerald just explained how different types of stars have different color, and that color helps us classify them. Tells us a lot about their predicted lifespan and their predicted temperature. So that's the real deal. And although we do have some artifacts in this camera, but you have to zoom in to see them. I have some deep red hot pixels that we always make fun of when we zoom in. The telescope that we're using is Chabot's 36-inch in diameter research telescope that we fondly call Nellie. And Nellie is a Cassegrain telescope. Means that there is a big mirror at the back of the telescope. There is a hole cored through that mirror, which is where the focus tube and eyepiece receives its light. And there's a secondary mirror up towards the front that bounces the light back from the primary mirror into either the eyepiece or the camera that's mounted behind the telescope. So I hope that answers that question.
Somebody asked, how much did the telescope cost?
Yeah, I wasn't going to answer that because I don't have it.
Well, we got a bargain. We got a heck of a bargain on this telescope. So the telescope actually cost Chabot a little less than $400,000. But if you had tried to buy a similar sized telescope in a similar configuration at the same time, it would have cost you $1 million and maybe more. And the reason we got such a good deal is because the telescope was designed by an engineer here at the Chabot Space and Science Center. He was working here at the time, and he did a lot of the fabrication work of the telescope. In addition, one of the most expensive components of a big telescope like this is that primary mirror that Richard was talking about. That mirror is 36 inches in diameter, it's 5 inches thick, and it has to be very carefully ground and polished in order to function correctly and give us nice sharp images. Typically, that's one of the most expensive components on a telescope. We got ours for free. What happened was that the Lawrence Livermore National Lab heard that we were in the process of building a telescope, which was originally designed to be a 1 meter telescope. But they said, hey, we've got a 36-inch mirror sitting in a box, in a warehouse that we've never used. It was intended originally for one of their nuclear testing programs, but the program got canceled. The mirror never got used, so it just sat for quite a while in their warehouse. And they said, if you want it, it's yours. And we said, yes, please. And it was a relatively easy thing to modify the telescope for a 36-inch mirror instead of a 1 meter mirror. 1 meter is about 39.3 or so inches. So it wasn't too much of an adjustment to make it a 36-inch telescope instead of a 1 meter telescope. So with all that, we got a heck of a bargain. Might also mention that the money to build the telescope was donated primarily by a guy named Merrill Martin. And Merrill Martin's grandmother and daughter are both named Nellie. And that's how Nellie got her name. So I wanted to just kind of pause here for a minute and just remind everybody, some of you, I think, tuned in a little bit after the start here. We want to encourage you to donate and help support our programming here. In order for us to keep these programs free and make sure everybody still enjoys them, especially during the period when we're closed because of the pandemic, we do need your support. So if you can donate, either on the Facebook page, you see a link there near the top of the comment section, or you can go to the Chabot Space and Science Center website, chabotspace.org. There's a donate button there. Click on that and help us out. We'd really appreciate it. All right.
Now we have another question here. This is going back to our planets.
Okay.
Jasper asked, will there be times when Mercury is visible? Well, you'll never see Mercury through this telescope, but because we don't like putting it so close to the sun. But the way to observe Mercury is to look on a star chart or a planet ephemeris and see when it is farthest from the sun. And either the good viewing for Mercury will be early in the morning, just before the sun comes up, or in the late afternoon when the sun comes down and Mercury is setting behind it. And then you could point a telescope safely in that direction and take a look at it. You always have to be careful looking at Mercury because sometimes it's very close to the sun and you don't accidentally want to nudge the telescope into the sun while you are looking through the telescope. You could do some serious damage to yourself. So if you've got, a good solid way to mount your telescope and you have a good way to point it to the right location without worrying that the sun is going to come into view, then it's always interesting to take a look at, but you have to be careful.
Yeah, and the other thing is, because Mercury is always so close to the sun, once the sun sets at the right time when Mercury's in the right place in its orbit, you'll see it above the horizon. But it's so low in the sky, this telescope actually can't go that low. So, so I see there's another question here about the Pleiades, whether or not it's visible tonight. And yes, the Pleiades are up. Pleiades is another open star cluster like M37. It's a bit closer. It's about 420 light years away. But the problem with the Pleiades is it's a pretty big cluster, and our telescope field of view is pretty small. So if we pointed it at the Pleiades, we'd see a few of the stars in the Pleiades, but we would not see the whole cluster. Pleiades is best photographed with a smaller telescope that has a wider field of view. Fun fact about the Pleiades. In Japan, the Pleiades is known as Subaru. And if you look at the emblem on the front of a Subaru car, it's the star pattern of the bright stars in the Pleiades star cluster.
Less so now than the older models.
Well,
All right. Well, that's pretty good. If you brought up a good point. People ask about looking at the Pleiades or looking at Andromeda, and it's the nature of this particular telescope that those are not really great objects to look at because we have such a long focal length. It tends to really not fit in the field of view, or just look like a fuzzy blob, or which two stars in the Pleiades would you like to look at? And but what we could do, Gerald, if you want to, is rather than try to show the Andromeda galaxy, we could either look at M32 or M110, which are next to Andromeda, and
Okay.
much more, easily resolved.
Yeah. Yeah. Well,
So
I'll tell you what. Before we do that, I saw a question on here asking whether any of the stars in this open cluster M37 are bigger than the sun. And the answer is yes. Actually, several of them are bigger than the sun. In particular, if you notice, some of them are blue in color. Those are more massive stars that are likely bigger in size than the sun. So hot stars show blue. They tend to be more massive than the sun, and therefore a little bit bigger than the sun. That's their advantage. Their disadvantage is they don't last long. A hot blue star, a massive star that burns hot and blue in color, goes through its fuel very rapidly. So a star that's maybe 4 or 5 times more massive than the sun, it's really bright and it's much bigger than the sun, but it may only last a couple of 100 million years, whereas the sun's going to last probably around 12 billion years. So, small is sometimes better. All right. So we're going to go, what, to 110, you think?
yeah, we could try 110 or 32. Let's try 110 first.
Okay. Let's see. I got to get back in that part of the sky again.
I keep making you jump around. Yeah.
You didn't plan this very well, did you?
No, I didn't.
Okay, I'm gonna go to a stop-off point here, and we'll resync the telescope. A few clouds up in that part of the sky, but we'll see what we can do here.
We'll see if we can do it.
Let's go to live view so we can synchronize the telescope. Oh, look at that, double star.
Oh yeah, look at that. That's pretty neat.
This is cool. We might actually stop and talk about this for a second.
I think that's a good idea. And I can also see if I can change the focus or make it a little bit better while you're doing that.
Yeah, a little bit better. Yeah. So you notice these two stars are not the same color and they're not the same brightness. This is called Almach. Almach is in the Andromeda galaxy, or not the Andromeda galaxy, it's in the Andromeda constellation. Thank you. And the difference in color is a function of the temperature of the star. So the blue star is the hotter of the two stars. The yellowish orangish kind of star, that is a much cooler star. And as you can see, it looks a lot brighter. And that's because that star is actually already approaching the end of its life and it's swelled up. So what happens is you have a star that's maybe fairly hot in the prime of its life. But as it grows old, it swells up, gets very big, just like some men get big when we get old. And as it grows larger, the outer surface cools. And as it cools, the color changes and becomes more yellowish and then eventually orange and becomes what we call a red giant. So what you see is a star that's probably still pretty much what we call a main sequence star, the blue one. It's massive, so it has a blue color. And then you see another star that's come off the main sequence and it's now starting to approach the red giant phase, which is, the beginning of the end for a star. So that's Almach. And from there, it's a pretty simple jump, I think, to M110 we're going to go to, right?
Yeah, let's try 110. 110's a little more impressive looking than 30.
All right, here we go. All right, we should be there.
Good.
So this is going to take a little bit of an exposure. This is a galaxy. It's very close in terms of the line of sight. It's very close to the Andromeda galaxy. Andromeda and M110 and M32 and the Milky Way are all part of what we call the local group of galaxies, sort of a group of galaxies that are sort of clustered together. When we look at the universe in the big picture way, we see that that's pretty common. Galaxies aren't universally spread out nice and evenly. They actually cluster together in knots and streams and strings of galaxies. It's kind of like looking at soap bubbles.
I don't know if I'm seeing it.
Well,
it could be.
Maybe a hint of it right there in the middle.
Yeah, maybe. Let me try doing something here. Let's go. Let's go do this. Yeah, that could be it. That could be the core. Let's try a much more sensitive setting here.
Okay.
Because I think we had to do that last week when we were looking at one of the other galaxies.
Yeah, if I use my averted imagination, I think I can see the shape of it a little bit.
Yeah, me too, now that I'm staring at it for a bit. Yeah, I'm thinking that maybe its orientation is like this. But we'll see. Oh, hold on. Don't panic.
That wasn't right.
Hold on.
It's in there. I see it.
Yep, I do too. Not very impressive view, though.
Yeah. Oh well.
Yeah.
So you can always point at the core.
This is the core of it here, and
yeah.
It's oriented like this, but you really can't tell.
Yeah. So M110 is about 2.6 or 2.7 million light years away, whereas M31 is about 2.5 million light years away. So M110 is a little bit farther away. Now, if you want, I can point at M31 just so we can image the core. We can't do the whole thing.
M32 or M31? M31. Okay, sure.
I can do M32 also.
M32 is much more of a spherical blob, so it might show up well. Could try them both.
All right. Well, let's try M32. All right. Here we go.
Good.
So you're going to do another 35-second exposure?
Yeah, I'll do 30 here. Yeah, I guess.
I think we're looking through some clouds too here.
Yeah, it doesn't help. Yeah, we definitely are. Didn't bring the cloud filter with me tonight.
Yeah. So M32 is even a little bit farther away. It's about 2.9 million light years away.
Let's see if we can see it. 2.9 million light years away. See if we can see it. 2.9 million light years away. 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 2.9 million light years aw Yeah.
Oh,
All
there you
right.
go. There
Good.
you
So at
go.
least we got something tonight.
Yeah.
There we go.
Yeah. So we're not seeing the whole galaxy. We're seeing the core and some of the spiral arms, but they're pretty faint, hard to resolve here. The way to really do this is to
There we
take
go.
many pictures uh, and then stack them together so that you get rid of a lot of the noise and bring out a lot more detail. And of course, if you use a different kind of camera that's even more sensitive, you get even more detail.
Yeah, but that's not bad considering the conditions here that we're
Yeah.
going through.
So
So
this, like I say, this is about 2.9 million light years away. On the sky, it's very close to M31 and M110, the one we were looking at a couple of minutes ago. Um, and like I said, they're all part of the local group of galaxies that our Milky Way belongs to. All right.
yeah, why don't we do the core of M31 now?
All right.
So that way people could say they saw part of Andromeda. So Andromeda is 2.5 million light
Oh,
years
you
away.
know what?
Right.
my
Don't.
computer. We are looking at the core of M. The two of
We've
them.
done it to them twice tonight.
The two of them are so close together that when I clicked, trying to click on M32, I accidentally,
Clicked on
I guess
F31.
the computer couldn't decide which thing I was clicking on, so it said, "Oh, he must be pointing to M31." So
I was kind of surprised by the brightness of it, but I said, okay, well, whatever. I'll take what I could get.
and there's this little window that tells me what I'm pointing at. If I had bothered to read it, I would have seen that.
All right, well, let's talk about Andromeda for a bit, since that's what
Okay.
everybody is really looking at. Actually, you
Okay.
know what? I could fool everybody. I'll do this. And now I'll say, okay, now we're looking at Andromeda.
Yeah, there you go.
Yeah. So 2.5 million light
Yep.
years
Two
away.
and a half
And
million. Yeah.
it's the giant cosmological train wreck that we're, as residents of the Milky Way, we will experience in several hundred thousand
Actually,
uh,
about 3
3
billion
million
years.
years.
Yeah, three
Yeah,
billion years.
several
Yeah.
hundred thousand, 3
Yeah.
billion years. And what's interesting about galaxy collisions is that they're very frequent in the overall scheme of things. Stars very rarely collide with one another. When they do, they tend to be fairly catastrophic events, not only for the people living around them, but also for observers. Will usually detect it as a fairly cataclysmic astronomical event, maybe forming a neutron star or a large explosion, or something along those lines. But galaxies are always colliding with one another, and we see all kinds of galaxies in the night sky that show evidence of those collisions. They're maybe have a twisted look to them, or they have streamers of stars that have spread out from the spiral arms of the galaxy into another neighboring galaxy. And that's the kind of thing that's going to happen when the Milky Way and Andromeda collide. It's going to be a fairly ephemeral event. The galaxies tend to pass through one another because, like I said, stars don't collide very often because there's a lot of space between stars. But so that collision between Andromeda and the Milky Way will disrupt the shape of the Milky Way, but it's not going to be like two trains hitting one another, right? It's just they're going to pass through one another, kind of like think of two clouds of bees going in opposite directions and passing through one another and continuing out the other side. And that's what a galaxy collision kind of looks like.
So I've got an image to share here, if we can.
Yeah, go for it.
Just to make everybody realize how poor an image we're actually seeing right now. So here's an image of M31. the Andromeda Galaxy. This was taken by a much smaller telescope, which has a wider field of view, and this is probably a stack of several exposures. And so you see a whole lot more detail. What we're seeing with this telescope, with our telescope right now, is just this central part around the core. So you're missing all the good stuff out here.
And you could point out the other two galaxies that we were trying
here's
to.
M110 and here's M32 right there.
Right, and 110 was kind of a bust, and maybe we'll try for 32, but you could see that they're much, much smaller.
Now, one of the interesting things about M31, it's actually quite big on the night sky. It's the most distant thing you can see with your naked eye. So if you were to find yourself a really dark sky location, get up in the mountains far away from city lights and things, especially in the fall, September, October, November, that time frame, you should be able to see it. It's very faint. It's a little fuzzy oval up in the sky. And if we could somehow turn up the brightness on M31, you would be amazed at how big it is on the sky. If you imagine a full moon on the sky, you're looking at it with your naked eye, the size of that full moon, it takes 4 full moons lined up to be as big as the Andromeda Galaxy on the night sky. So it is actually a quite large object, and that's why we can't see the whole thing in our telescope field of view. Our field of view can't even cover the full disk of the moon. So when you're talking about something that's 4 moons wide, we're not going to see any but a very small portion of it. All right.
Got 3 questions here. And one of them is really a great question, or they're all good questions, but this one's really it jumps out at me. If the universe is expanding, how could galaxies collide? And because you would be thinking that all galaxies would be moving away from one another. So the way to think about Andromeda and the Milky Way is that it's a local effect. If you were 100 million light years away from the Milky Way, looking back at Andromeda and the Milky Way, the entire local cluster of galaxies, Andromeda, Milky Way, M33, M110, M32, they'd all be moving away from where you are. The entire cluster would be moving along with the expansion of the universe. But since the Andromeda galaxy and the Milky Way are gravitationally bound, we're kind of orbiting one another, right? We're not necessarily more affected by the expansion of the universe than by our own local effects on one another.
Yeah, the force of gravity is actually stronger than the expansion of the universe on a local scale. So that's why stars stay within our galaxy and galaxies within clusters like the local cluster. They are gravitationally bound to each other, and that gravitational pull is stronger than the force, if you will, of the expanding universe. But on a grand scale, a universal scale, the universe is expanding, and these clusters of star or galaxies are moving away from each other, and that's been measured and documented many different ways. So we know it's happening. There was a question that I saw that Andromeda would collide with our galaxy in about 5 billion years, which is about the time when we expect the sun to sort of reach the end of its life. And part of that question asks, well, that's about the time when the sun will explode. Sorry, the sun will not explode. The sun's going to die in a very slow process, resulting in a white dwarf and a planetary nebula. It will not explode in a supernova. In fact, most stars do not die in a supernova explosion. They die in that very slow process that results in white dwarfs and planetary nebula.
Well, nonetheless, it's not going to be a very pleasant situation here on Earth So it'll probably be a good time to move to Andromeda.
Well, you may not have a choice.
Right. That's right.
Yeah. So as Richard said, the chances of actual collisions between objects during this collision is actually pretty small. But it is possible that the Earth, its orbit will get disrupted around the sun, and that the sun's orbit around the galaxy is going to get disrupted. So, and that's actually likely to happen before our sun reaches the end of its life. So something to look forward to. Mark it on your calendar, and you can observe it and see how it works out.
Hey, Gerald, who took this photo? This is really a great photo of
Andromeda. I don't know. I think it was one of the EAS guys. I want to say Bill Drilling.
Oh yeah, this looks like maybe it was Bill's photograph.
Yeah,
this is
I won't
quite
swear
good.
to it.
I'll have to ask him if it was his.
Yeah. And then another question somebody asked, is there a singularity at the center of the Milky Way galaxy? And the answer is yes. We think there are black holes, singularities surrounded by a black hole at the center of most galaxies. We know there's one at the center of the Milky Way, and we're certain that there's one at the center of Andromeda, and probably most of the other galaxies that we see have black holes surrounding a singularity at the center of the galaxy.
Stephen
question
asked
about your camera.
Yeah, I had a camera question. The camera we're using here is a Canon T1i. It's an older model EOS DSLR, and it's got like 10 megapixels. It's nothing impressive in terms of the number of megapixels. But what's nice about this camera is that it matches this telescope better because it's got bigger pixels. And when you have a long focal length telescope, having fewer larger pixels is actually advantageous.
Well, Richard, it's shortly after 10 o'clock. For those of you not aware, the rules changed recently in Alameda County for COVID prevention. And one of those rules says that we need to close up here at 10 o'clock. So we're going to have to wind it up here. But I do want to remind everybody, first of all, I hope you enjoyed yourselves and had a lot of fun. But we want to remind everybody that we are have a donation program right now, and also a membership drive. So if you were to go to the ChabotSpace.org website and join as a member, for every member that joins or new member joining between now and December 31st, we're going to add a membership to a local teacher. So we really hope you'll support us. Even if you don't want to become a member, if you just want to donate, we would really appreciate it. You'll help out all of our STEM education programs, our virtual programming, and so on. And so we want to really encourage you to either donate it with the donation button on the Facebook page, or go to ChabotSpace.org and hit that donate button at the top of the page on our website and help us out. We'd really appreciate it. All right. So I think that's about it, Richard.
All right. Okay. Well, thanks everybody for joining us tonight. It's as we get later in the year here, some of our winter constellations are going to be a little more prominent in the sky, and we're getting pretty close to being able to look at things in the constellation of Orion, which will be nice. It's just starting to clear the dome. And so maybe even next week towards the end of the program, we'll be able to take a look at the Orion Nebula. Maybe.
Yeah, might have to wait 2 weeks, but won't be too long.
It's getting close. Yep. All right. Anyway, take a nice look at the night sky during the week. Enjoy your Thanksgiving and stay safe. And we'll see you next time.
Next Saturday at 9 o'clock. See you then.